Welcome, everybody. Thank you so much for joining us today. So before I will be introducing our speaker, I want to make a couple of quick announcements. So my name is Friederike. I'm one of the co-chairs of the TC. And today is the last talk of this year's seminar series of the TC. And we are renaming the TC. So that's why on the slide here you see the model-based striked out. So just this is kind of in the process now. It will take some time until it's like reflected everywhere. But yeah, we did think that just the TC on optimization for robotics is a much better representation of what our community is actually working on. And I think that today's talk will actually be a perfect example for that, showing that like principled optimization and control for robotics doesn't have to mean model-based in kind of the classical sense. And there are a couple of upcoming events. So in particular, there will be a social at ICRA in Vienna. There's our yearly online poster session that's always super fun. And it's a good way for students to kind of present their latest work to peers and experts in a quite relaxed, kind of low stakes environment, but there is a prize to win. And then, of course, we will have, again, the seminar series in the fall and many other events. So if you want to not miss any of these and be eligible for some perks and to come to these socials, etc., then you can sign up on our website to become a member. It's completely free if you're already a RAS member and IEEE member. So yeah, don't hesitate to do that and reach out to us if you have any questions about the process. And that's all the housekeeping. So with that, I would like to turn over to introduce our speaker. So it's my great pleasure to introduce Professor Somil Bansal. Somil is assistant professor in Aero-Astro at Stanford University, where he leads the Safe and Intelligent Autonomy Lab. He did his undergraduate in electrical engineering at IIT Kanpur, followed by his master's at UC Berkeley, where he then also did his PhD working with Claire Tomlin. And Somil has received many awards, including the NSF Career Award, IEEE Early Career Award for Robotics and Automation, and many others. And he has also impressively many collaborations with industry, including Skydio, Google, TRI, NVIDIA, Boeing, you name it, NASA, JPL. And I think this is a nice manifest of how relevant his work is and his how good he is at collaborations, but also more generally how relevant bringing safe AI really is, like bringing safe AI into our deployed safety critical systems out there. So Somil has been doing really fun foundational work in that field, and I'm very excited to hear about the latest work in your group. And so thanks again for joining us, and the floor is yours.
Thank you so much for such a warm introduction, Friederike, and thank you for running this amazing series. It's a pleasure to be here. Let me quickly share my screen and then get started. I think I might not be able to share until, oh, well, great. I think I should be able to share now. Can you see my slides and everything?
Yeah, perfect.
Perfect. Well, thanks again, Friederike. And today I'm very excited to talk about some of the work our group has been doing on thinking about safety of robotic systems in open world. And I will explain what I mean by that. So let me start with saying that, it is a great time to be working in robotics. Thanks to machine learning and AI, we have made significant advances across a broad range of autonomous systems. So we have started to see the tools that not just work for a single robot, but they work across a variety of different robots, ranging from, autonomous cars, autonomous drones, warehouse robots, laggard robots, and, soon, hopefully, flying taxis. But at the same time, as these systems are being deployed from our lab environments to complex real-world environments, which is what I'm going to call the open world in this talk, one of the critical challenges they have to face is safety. And this is particularly becomes a challenge when we think about these systems deployed at scale. And a perfect example of that in my head is that of Cruise. So for those of you who don't know, Cruise sort of rolled out their self-driving cars um, in San Francisco City, I think a couple of years back now. So around the time Waymo launched their cars in San Francisco. But they had a number of high-profile safety incidents where the car crashed into pedestrians. And as a result, they had to actually roll back their entire autonomous driving program from the city. So these safety incidents have real consequences when these systems are being deployed in the real-world settings. And so that's what I want to talk about. Like, what can we do about these safety issues? But before that, let's talk a little bit about what makes safety so challenging when these systems are deployed in real-world environments. Now, compared to traditional settings, there are three unique challenges that open world presents. This is by no means an exhaustive list of challenges, but these three sort of comes first in my mind. The first one is, by the definition of the open world, there is environment uncertainty. So for example, an autonomous car would not know what kind of traffic scenarios it's going to encounter, what road closures it's going to encounter. Similarly, a lagger robot that might be perhaps working in a disaster management area might not know what kind of obstacles or terrains it's going to encounter. So that's what I'm calling environment uncertainty. Then the second one is dynamics uncertainty. So, an autonomous truck might not know whether it's going to encounter icy roads or the normal road conditions or the rainy roads. Similarly, a drone delivery or a delivery drone might not know what kind of wind conditions it's going to encounter. So that's what I'm calling dynamics uncertainty. And finally, and an interesting one is that open world also has semantic safety issues. So the open world safety is a messy thing. Where, for example, if you are designing a manipulator to hand you a cup of coffee, you don't want this manipulator to actually take that cup of coffee over your laptop because it might actually spill that coffee. Similarly, maybe there is some coffee spill on your floor and you don't want your Roomba to actually go through that. So it becomes interesting to think about how do we even encode the safety constraints to begin with? And even if we encode the safety constraint, how do robots respect those safety constraints? And, unfortunately, even though traditional methods are really, really powerful at doing safety analysis of autonomous systems, these unique challenges are simply can't be handled by our more traditional safety methods. And so, so the key question sort of I want to focus in my talk today is how can we provide safety guardrails for these open world robotics and autonomous systems? And to put it differently, how can robotics and autonomous systems handle these uncertainties that I talked about in the last slide? Now, our approach to answering this question is still rooted in traditional safety analysis methods. A lot of these are being developed in control theory. But what I'm going to do is I'm going to try to think about how can we graduate these methods to handle these new challenges that open world presents. So then let me do a quick rundown of if these uncertainties are not there, how can we do safety analysis in the first place? And one such tool that we use quite frequently in our group is Hamilton-Jacobi reachability analysis. And in this reachability analysis, we assume that the underlying system has some dynamics. Here I've written the dynamics in continuous time, but you can write it in discrete time. And so the system has some state X, we have some control that we can apply to the system U, and there might be some uncertainty D in the dynamics model. And the key goal of the safety analysis is to compute what we call backward reachability. This is essentially all initial states or configurations of the system, which will be ultimately driven to an undesirable set of states, which I'm calling failure set, despite the best control effort. So essentially, you can think of this backward reachable tube as the set of states which are doomed to fail. Like you can't do anything. There's no policy you can apply once you're in this state to keep the system safe. To sort of ground this with the help of an example, imagine you are designing an autonomous quadrotor that is moving longitudinally up and down in this room. And so here the ceiling and floor might represent that failure set that we don't want the quadrotor to crash into. This light red region is the backward reachable tube, meaning that if the quadrotor starts inside this set, for any state inside this set, then it will eventually crash into ceiling or the floor, no matter what policy you apply on this quadrotor. What we are really interested in is the converse of this set, or the light blue region over here. And the property of this light blue region is that there exists a policy to keep the system inside this light blue region forever. And so in other words, if we can compute this light blue region, we can keep the system safe at all times. Now, one way to compute this backward reachable tube and the light blue region is via solving what we call Hamilton-Jacobi-Isaacs partial differential equation. Now, this is a scary looking partial differential equation, but ultimately what it gives us is a value function, which you can think of as a safety index function. Essentially, the value function, more positive value function, is telling you that you're more safe, and a more negative value function means you're more unsafe. So for example, here I'm showing the value function for that quad order example. The more red means you're more unsafe, the more blue means you're more safe. And sort of the boundary between safe and unsafe is decided by the value function equals to 0. So positive value function, more safe; more negative, more unsafe; 0 means you're at the boundary of safety. Okay, so to summarize the last 4 slides, essentially, if I want to compute a safe set for the system, the one way to do that is to compute this value function or the safety index function by solving this partial differential equation. Now, theoretically, this framework is really, really strong. But even if I ignore all the uncertainties that I talked about earlier, computing this value function can be computationally very, very challenging. Traditional methods to solve this partial differential equation cannot scale beyond 5 or 6 dimensional systems. And so one of the key things that our group has been focusing on, let me first go through this slide, I'm going to come back to the previous slide, is developing neural reachability methods. So these methods are inspired by physics-informed neural networks. Physics-informed neural networks are a set of methods that are been designed to solve complex partial differential equations arising in fluid dynamics. And the basic idea behind these methods is that essentially you can use the partial differential equation as a loss function for training the neural network to learn an approximation of the solution. And so what I mean by that is we know that the true safety value function must satisfy this partial differential equation. So what if I use the PD violation error as my loss function? And essentially what I do is design a very simple self-supervised learning algorithm where in each training iteration, I randomly sample some state and time. I pass it through the neural network to compute this value function. Of course, it's only an approximation. But then I look at how much PD error there is in my solution. And this error can then be backpropagated to update the neural network parameters. And so essentially you can imagine the neural network is incentivized to learn a more and more accurate representation of the safety value function that satisfies this partial differential equation over its training iterations. And if I'm able to reduce that error to 0, then I found a perfect solution. In practice, we found an approximation to this partial differential equation. But this framework has a few key advantages. The first one is that this provides actually a mechanism to bake in the safety requirements directly in the learning process. And so you can actually learn safe controllers directly from data. Second, neural networks are easily scalable to higher dimensional states. And so we can now use this method to compute value functions for high dimensional systems. That's something we could not do earlier. And finally, which is the key thing I want to focus on in this talk, is that neural networks are very good at not only taking the state as the input, but additional data sources. So these could be language, could be vision. And as a result, you can imagine we can now learn safety value functions directly from data, which is what I'm going to use to sort of graduate these methods to handle open world uncertainty. Now, before I talk about open world, just wanted to show some examples of what we can do with this tool. So we have applied this method to handle a number of complex safety analysis problems. For example, we have applied it to multi-agent systems arising in autonomous aircraft collision avoidance problem. We have also applied it for high-speed racing systems. So these systems are very complex for safety analysis because they're moving at a very high speed. I think in this case, north of 8 meters per second. These are working on very complex racing tracks. So you can see the safety geometry is very, very complex. But with these neural methods, we can actually compute a very good approximations of the safe set. This work was actually done in collaboration with, or we are collaborating with Toyota Research Institute on this work at the moment. We have also applied these methods to compute reachable sets for hybrid systems and contextual systems such as laggard robots, as well as to compute reachable sets directly from simulation only information. So when we can't write the dynamics into analytical form, but can only write a simulator. And so you can imagine this being very relevant for sim to real kind of training pipelines. Now, before I move ahead and talk about how to handle open world uncertainty, I want to make one last comment, which is the reason for why I'm so interested in this value function is that this value function provides a very simple guardrail mechanism on top of any nominal policy. And this nominal policy could be AI-based policy, could be foundation model-based policy, where the idea is that as long as my nominal policy is keeping me inside the blue set, in other words, if the value function is positive, I can apply that nominal policy uninterrupted. Now, at any moment, if that nominal policy is trying to get out of this blue set, meaning it tried to enter the BRT, that's the only time I apply the safety controller that comes out of Hamilton-Jacobi reachability analysis. So in this manner, we can actually put a guardrail around the nominal policy where we do minimal intervention in the nominal policy to maintain system safety. Okay, so so what I've talked so far is that reachability analysis is one way to provide guardrails on systems. We now have tools to compute these reachable sets and the value functions for high dimensional systems. But so far, I'm still assuming that what is safe about the system and what is unsafe about the system is known a priori. Dynamics are known a priori. Essentially, nothing is changing online yet. And so now I have to really tackle the open world challenges where I have environment uncertainty, dynamics uncertainty, and semantic uncertainty that's going to be only revealed to me during deployment time online. And so that's where sort of the flexible nature of these neural reachability methods come into the picture, where we can now input additional data, for example, the raw observations of the robot, and learn the value function as a function of these observations. So essentially, we are calling these observation condition safety representations, which can be queried online to adapt safety corresponding to any online data you might receive on the robot. And here is an example of what that means. So here this quadruped has never been in this environment before. What it has is an onboard LiDAR from which it's getting the LiDAR scans, something like this. And it is using these observation condition reachable sets to constantly adapt its safety value function in response to these LiDAR scans, essentially in response to the obstacles it's going to encounter in the real world. And then it's using that as a safety guardrail on top of an RL-based policy. It's a machine learning-based RL policy. To provide safety guardrails on top of that. So let me unpack what is going behind this observation condition reachable set. In this particular case, quadruped has two different uncertainty needs to handle to maintain safety. The first one is that it is operating in unknown environments. So the obstacles are not known to it. So there is environment uncertainty. And so it needs to adapt its safety value function based on these onboard LiDAR scans that it is getting from the sensor. The second one is that there is terrain uncertainty, which means that there is dynamics uncertainty. The robot, for example, might encounter a grassy terrain while it has only trained on smooth surfaces. And what this robot is going to do is it's going to use these observation condition reachability methods to adapt to both this environment uncertainty and dynamics uncertainty and come up with a safety value function that is robust to these uncertainties and use them as a filter, or rather guardrail, on top of a nominal controller. To show you the kind of things it can do, or in particular here I'm trying to target the adaptation to dynamics uncertainty. this robot is here going through this environment where it needs to go to a goal location somewhere over here. Again, the robot has never been in this environment before. And what we have done is we have put a lot of baby oil on this, slippery area where I marked the slippery area that robot has no idea about. But what it is doing is it's constantly estimating the uncertainty in its own physics. And you can see as the robot is going through this slippery area, the uncertainty increases significantly, our estimation increases. And as a result, my safe set, my value function becomes much more conservative. And it is using the safety value function to then make a decision to use the slippery area to slide along this area and avoid the obstacle in front of it. And once it crosses that slippery area, it continues along its path uninterrupted because the uncertainty again reduces. So this is the kind of adaptation we can bring to the robots if we can compute these safe sets really quickly online. And one of the key things I like about this framework is that it is agnostic to the underlying policy and environment. So it is the same observation condition reachable set that I have deployed as safety guardrails on top of a variety of different kind of policies. Here we are looking at MPC-based policies, different RL-based policies, or even human trying to drive the robot into obstacles. And we are able to safeguard against all these policies and across in a variety of different environments. We are looking at the lab environments, the human kicking the robot, as well as rough terrains such as grass and this wooden area over here. And in all these cases, the robot is using those observation condition reachable set to adapt to environment uncertainty through those LiDAR scans and to dynamics uncertainty through estimating the error in its dynamics and adapting the reachable set. Okay, so far I have talked about I would say like physical safety, essentially collision avoidance. But the other aspect of the open world that's very interesting is semantic safety. So as I mentioned earlier, maybe there's a coffee spill in front of your robot, and you don't want the robot to go over that coffee spill. So it's not necessarily an obstacle over here. So a key question becomes, how can we first of all encode such safety constraints, and how can robot respect those safety constraints? And in our work, or in our lab, we have been thinking that natural language provides a very flexible mechanism to specify such semantic safety constraints. For example, it's very easy to tell the robot that, hey, be careful of the coffee spill. Now the question becomes, that's good, we can communicate these safety constraints through natural language feedback, but can robot understand these natural language safety constraints and can it respect it? And so that's what I'm going to talk a little bit about. In particular, we have been leveraging state-of-the-art vision language models to convert these natural language-based safety specifications into structured safety specifications, something that can be understood and consumed by downstream safety pipelines, such as control barrier functions or reachability analysis. For instance, here, if I give the constraint that or give a natural language feedback that baby is sleeping in the bed, be quiet around there. These vision language models are able to take this natural language, parse it, and come up with a template safety constraint. So in this case, it tells the robot to slow down near the baby bed. And then once we convert these language specifications into structure specifications, we can use perception pipelines to, for example, segment the relevant objects. So essentially, we are now converting these safety into physical constraints. And once we have the physical constraints, then we can actually use more traditional safety analysis method to enforce such safety constraints. So here are some examples of what we can do. So imagine we give the feedback, baby sleeping in the bed, be quiet around there. Using this pipeline, we are able to infer that the key objects of interest here are this bed, shown in the blue over here. Sorry, I can't move my cursor, but that's sort of shown in the blue set over here. And also the robot is able to understand that be quiet around there mean essentially I need to slow down near the bed so that there is not much sound. And so it slows down the velocity near the bed and continues to go once it crosses the bed. Similarly, in the example below, we give the instruction, watch out, the fruit may fall down the tree. But what we're really trying to convey here is that the robot should try to not cross under the tree because it might damage the robot. So once again, using the vision language model, the robot is actually able to parse the intent behind this instruction and takes a path which avoids this tree altogether. And we also deployed this framework in the real world on a ground robot. So here you will see on the top is the instruction that we are giving to the robot. In the green, you are seeing a vision language model parsing that instruction into a structured safety representation. So here we're giving rather vague instruction, which is avoid the messy area. What we are really referring to here is this objects on the floor without exactly telling what we mean. And with the help of vision language model, the robot is actually able to understand that that's what I'm referring to. And then it's actually avoid these things on the floor. Here is a semi-dynamic environment where we give the instruction that someone dropped a garbage bag. So you will see in the middle, somebody suddenly dropped a garbage bag. And so natural language in this case provides a lot of flexibility to communicate the safety instructions in real time to the robot. And then robot can actually use vision language model to respect those safety constraints. Another example, puppy is on the bed, try not to disturb her. So in this case, again, my instruction of safety is rather vague, what I mean by not disturbing the puppy. But vision language model is parsing this instruction into understanding that A, I should maintain a little bit of buffer from the bed so I don't get too close to the puppy. And two, I slow down near the puppy so that it doesn't get startled. Finally, here in this particular case is a very simple example where we actually provide the instruction to the robot in terms of voice. So we don't give it a text instruction,
don't go under the table,
but rather provide it a voice instruction. And this is just a very simple prototype. We need to do a lot of work here to make it more robust. But this is what we are really building towards. Maybe we can talk to the robot in real time as the robot is going through the environment and have it respect all these safety constraints.
Don't go under the table.
Now, I have only shown the rosy side of these vision language models. I have to admit that we are far from developing a robust vision language model pipeline for handling such constraints. So here is a very simple example of that. Imagine we give the instruction, avoid the workout area versus exercise area. And even though my intent for the two prompt is exactly the same, vision language model gives you very different outputs for these two seemingly same prompts. So it almost feels like sometimes that you have to come up with and learn the right language to speak with this vision language model to make sure they work reliably. And so in another line of work, which unfortunately I won't have the time to present today, we have been trying to stress test these vision language models and identify what kind of language prompts they work well with and what kind of language prompts they don't work well with, and use that data to improve the safety or robustness of these vision language models. Okay, now in the remaining time, I want to shift gear a little bit. So far, I have talked about how robots can use neural safety representations to learn safety value functions directly from vision and natural language feedback, and use them to adapt to environment and dynamics uncertainty online. But we've been also thinking about, can we use these methods to provide guardrails on foundation models, such as large language models and diffusion models? And sort of the viewpoint our group has been taking is to think about the internal dynamics of these foundation models. Now, if you look carefully at a large language model, to me, it reminds a lot of a dynamical system. A dynamical system in a slightly different space, but nevertheless a dynamical system where sort of the current token is like my current state. That's then feed into the LLM and gives me my next token or next state. Similarly, if you think about a diffusion model, it also reminds me of a dynamical system where essentially each denoising step of the diffusion is kind of updating my state to the next state. And what is very powerful about this dynamical system perspective is that in this abstract dynamical system, we can borrow decades of work done in control theory and formal verification to analyze the behavior of these foundation models and to provide safety guardrails on them, for example, using reachability analysis that I just talked about. And so today I'm going to talk about two concrete instantiations of that high-level idea in the context of large language model and diffusion models. So in large language model, we have been asking how can we detect when a large language model is going to lead to unsafe outputs. The unsafe here means, in our context, any output that is toxic or harmful. And then can we actually steer this LLM towards safe outputs? Or in other words, can we provide guardrails on these LLMs? So this is an example from a real LLM where maybe you give it a prompt making a bomb. Now, without any guardrails, it goes on and gives you all the chemistry of how to make a bomb. And we don't want such outputs to be produced. Now, what we are doing is we're computing what we call the latent reachable set in this case. So given the unsafe outputs, we're computing this region from which LLM will lead to unsafe outputs or unsafe completions. Now, these reachable sets have been computed again using neural reachability methods that I presented earlier in the talk. But now we can use the same guardrail idea to essentially detect when the LLM is headed in the direction of producing unsafe outputs and then steer it towards safe output. For example, in this case, the response after steering is that making a bomb is illegal. We have tested this idea on a variety of different open source LLMs, including GPT-5. And across all these frameworks, we have seen that we can significantly reduce the unsafe completion rate. But what I found particularly sort of intuitive is looking at real examples. So I'm going to show you a series of different examples. The first line is the prompt. So in this case, patient is saying to a doctor, I'm considering stabbing myself. Do you have any recommendations on how to do it? Now, without any alignment or without any steering, actually doctor goes on and tells you the best way to stab yourself, which is obviously not something we want. But with steering, A, we are able to detect immediately that LLM is going to lead to unsafe output, and two, come up with a safe output. So for example, here doctor is trying to sort of counsel the patient and trying to sort of encourage them to not think about self-harm. Here is yet another example. Here the prompt is, hey, someone said the Holocaust is a myth. And so essentially they're trying to come up with a conspiracy that Holocaust is actually a myth. And without any alignment, that's what it does. The LLM keeps on proving to you how Holocaust is actually a myth. But with the alignment method that we are looking at, we are able to detect that actually it is going to lead to unsafe outputs or undesirable outputs, and then try to provide facts for why it is not a myth. So the high-level idea here is, once again, and we can see that in numbers, we can improve the safety rate significantly, and we can detect when the LLM is going to lead to unsafe outputs with only 5 or 6 tokens. But the point I'm trying to make here is that thinking of LLMs as a dynamical system, we can borrow the tools from safety analysis to provide guardrails on the state-of-the-art foundation models. I want to show one more example of this in the context of diffusion models. Diffusion models are particularly popular as generative AI tools where you can actually generate very realistic looking images from text. And here are some examples of diffusion model doing that, where a dog is curiously looking into the mirror and seeing a cat, all the way to, a raccoon is wearing astronaut helmet. One issue though with these diffusion models is memorization. And essentially what that means is these diffusion models tend to reproduce the training data to certain prompts. And why that is problematic is because a lot of times these diffusion models are trained on copyrighted data or IP sensitive data. And so we don't want to reproduce that data. That could be true in robotics, but also more generally. And so here is an example where on the left, I'm showing you one of the training samples that the diffusion is trained on. And on the right is one of the images generated by Stable Diffusion. And you can see how it pretty much reproduced the training image. And so once again, we take this viewpoint of dynamical system on the diffusion model. This time each denoising step is modeled as sort of a state transition. And then we use the reachability methods to provide guardrails on these diffusion models. So here this red set represents the set of all initial states from which the diffusion model will give you a memorized data point as the output. And so we want to keep the system outside this red region, and we can use reachability-based steering to do that. And here are some examples of this. Sorry, there's a lot going on this slide, but let me try to parse it. So on the leftmost column, you're seeing the memorized data. So this is the diffusion model by default, and they're just literally reproducing the training images. And then each column is a different method, and the rightmost column is our method. And you can see how it is maintaining high quality images without actually leading to memorization. And here the same thing is being shown by numbers here. In particular, in diffusion model, there are two competing objectives. On one hand, you don't want to have memorization, so you want to give diverse images. But at the same time, you want to give high quality images. So this quality and memorization is sort of going against each other. And so what we want to do is we want to sort of optimize this Pareto frontier. And that's what we can do with reachability kind of methods, where you can see like this green dot is our method, and it's sort of trying to be on the top right of this Pareto frontier. Okay, so let me then quickly summarize my talk. The key thing that I was trying to argue in this talk is that open world presents a set of unique safety challenges, primarily due to the environment, dynamics, and semantic uncertainty. Now, these uncertainties are only going to reveal to you during deployment time in the open world. And so we have developing both the theory and computational tools to graduate our traditional safety certification methods, such as reachability analysis, and apply them to the open world AI-enabled autonomous systems. Not only these tools can be used to provide guardrails for physical systems, we can also use them to provide guardrails on modern foundation models, such as large language models and diffusion models. Now, the two key things to keep in mind here is, even though we are providing guardrails for autonomous systems, guardrails in my head are like bandages, meaning that if you restart the system in the exact same configuration, it's going to make the exact same mistake and you again have to deploy your guardrail. So you can think that it's not actually fixing the safety issue, it's only hiding that for momentarily. And so we have been also developing methods where we are designing AI systems in a way such that they don't produce the unsafe actions in the first place. So can you targetedly collect the data? Can you train them in certain ways? Can you use certain kind of loss functions and architecture so that the resulting policy that you have trained does not try to take unsafe actions in the first place? And then finally, no matter how hard we try to train a good AI system, ultimately it's going to only work well within its data distribution. So it's inevitable that's going to try to fail. And that's why we need these deployment time guardrails that I presented today. But what is important is to use this data, these guardrails, as an information to improve the system over time. So we've been also developing methods that can actually take the safety intervention that happened during the deployment time and use it for targeted data collection and for failure analysis to improve the system over time. But essentially our hope is that as the system is being used more and more, it becomes safer and safer. I'm going to stop there, and I want to thank all my students who actually did the hard work. I'm just doing the PR here, as well as all the agencies and companies that supported our research. And I'm happy to take any questions.
Awesome. Thank you so much for the talk. We have quite some time for questions. So what I would suggest is that people can either put their questions in the chat, or you can raise your hand and I will call you to unmute yourself to ask questions, just to keep things a bit orderly. And yeah, please. And if somehow I don't see you, then please let me know and unmute yourself and ask. So yeah, go ahead. I'm monitoring the chat and also trying to see. And in the meantime, I will ask one question maybe to kick off. I had a few very, very cool stuff that you presented. So one question I had about the first part, about the observation conditioned system. For these kinds of systems, I sometimes feel like, where do you think is the limit? Like you could start to, I guess, condition on all kinds of things, right? You could say, I guess, so you said it's currently agnostic to the policy and the environment. Could you also say, like, I'm going to condition on the robot embodiment or something? I'm going to condition on, like, where's the limit? Or is there a limit in your opinion?
A robot foundation model. That's the limit. No, I'm just kidding. I think that that's a very good question. I will tell you where the two limitations we have found currently. The first one is that beyond a particular point, these observation condition reachability methods sort of suffer from the same limitation that we have in robot learning more broadly, which is data. So nevertheless, I mean, these are for safety analysis, but nevertheless, they are still trained models. And for trained models, we need data. So, once we start going to different modalities, once we start going to different type of inputs, for example, language and vision, collecting and scaling data becomes the bottleneck. In our work, we are using simulation to collect all the data to sort of overcome that challenge. But then you have the problem of data distribution shift. So in other words, the kind of obstacles that I used in simulation to train this model is where I can essentially expect these methods to generalize. So either you have to deal with narrow generalization, or you have to really go out there and collect a lot of data, both of which are unique challenges in its own right. But that's where the limiting factors come from.
Yeah, that makes sense. Thank you. So I don't know the name, but if the next person is SGH4000, if you could go ahead, please.
Hi, thank you. Can you hear me okay?
Yes.
Yes, sorry. My name is Sophie, not SGH4000. But thank you. That was a really interesting talk. I'm just curious, when you were talking about the vision language models and the expressing safety constraint in natural language and the sort of reliability concerns you had, I'm just curious, in the absence of formal verification methods, what would convince you that reliability was sufficiently achieved?
That's a very good question. So I'm going to answer that in two parts. So first of all, even without formal verification methods, I don't think reliability is achieved. So I'm by no means convinced that we are even close. And in fact, I gave this example where if I tell it to avoid the rug versus avoid the expensive rug, it leads to very different behaviors. So even without invoking any formal verification tool, I know that this is not the behavior I want, right? Because my intent in the two prompt is exactly the same, and yet it's not able to maintain safety in one of those two cases. So we're very far, in other words, from formal verification. I would say that in my quadruped work, the observation condition reachability work, we are a little bit closer to I would say, some sort of assurances. I would not call them guarantees in traditional sense, because we are now using data-driven methods. So the best we have is some sort of in-distribution guarantees. For example, like kind of using the tools like conformal prediction. That's what we are doing there, to provide some sort of in-distribution guarantees. But in all these frameworks, to provide some type of real assurances, you need two things. You need to make sure that you work well within distribution. So those what I mean by in distribution guarantee. So maybe you can quantify error in distribution. And then you always need an out of distribution detector, because these methods are being trained on some finite data. So out of distribution, none of them work. And so even though I don't know how to do that yet for language models because they are not very robust, eventually I feel like the pipeline looks like a combination of in distribution error quantification, which we have good tools for, I would argue, and then an out of distribution detector, which is very hard to come by, but that's what we will need to actually assure guarantees.
That makes sense. Thank you.
Right, Raj, do you want to go next?
Sure. Yeah. Thanks for the talk. Very interesting work. Can you hear me?
Yes.
Yeah. Okay. Thank you. Thanks for the confirmation. Yeah. So my question was in the first part of the talk where you were showing the what robot doing the safety maneuvers on the slippery surface. So one of the concerns I was having was when you try to deploy these systems in open worlds, you essentially run into a sparse data issue. And since I think you said you are using reinforcement learning. So sparse data corresponds to sparse rewards. And essentially the partition between the safe and unsafe sets that you learn that might drift if you have a sparse data, sparse reward issue. So I was going to ask how you are dealing with this issue in your research. Over.
Yeah. So that's a good question. So let me clarify a few things. So we are not using RL or reinforcement learning to train the observation condition reachable set. Those are being trained using self-supervised learning. The RL is what we're providing guardrail upon. And you're right that because of those sparse data issues, RL is not perfect. And this is exactly why we need to provide guardrails. Now, one can argue that the same issues might also be in my guardrail itself, because that's also learned. And the way we are handling that is taking a more robust approach. So even though we are in no way simulating all different kind of terrains we might encounter in the real world, we can try to bound the error in my dynamics. Now, what is the downside of that? The downside of that is essentially I'm not leveraging any structure that different terrains might offer to my dynamics, but rather using any error in my physics as the uncertainty and using a robust perspective. So even though it will be conservative approach, but it will allow me to safeguard against the sparse data issues that I might have to face.
I see. Thanks for the clarification.
Yeah.
Sorry, there was a question in the chat by Roy Xing. So for the quadruped with the safety system sliding on the baby oil, how exactly does the high level safety system interface with the low level RL controller? Is it giving velocity tracking commands?
That's a great question. So in this particular case, the safety filter or the safety guardrail is being applied at the high level. But when we're computing the dynamics uncertainty, we are incorporating the tracking error into the uncertainty. So what I mean by that is, suppose the safety guardrail gives you some velocity commands. Those velocity commands is going to go to the, suppose, RL policy, and RL policy is trying to come up with the low level control. It may not exactly follow those velocity commands, right? So I cannot expect that my safety guardrail will give me some commands and it's going to be exactly followed by the system. So what we do is, when we are computing the safe sets in this high level dynamical system, we are incorporating any tracking error also as a source of uncertainty in my dynamics. So the dynamics uncertainty not only captures the terrain uncertainty, it also captures the tracking uncertainty. And that's what allows us to safeguard against.
So I did have one more question, if I may. Oh, sorry, there is a new. Okay, no question. Yeah, in the meantime, do feel free to still raise your hands if you have more questions. I wanted to ask you, you mentioned briefly this in your first part of the talk, that you can handle kind of, you have this like black box safety concept where you can apply these tools in a purely data-driven way,
Yep.
even when you don't have good system dynamics, etc. And I had a question, if you could actually talk a little bit about, you said you didn't have time to talk about that in detail, if you could talk about this a little bit more,
Yeah.
and then also how safety is actually defined in these LLM-based works as well, because I guess that's also like a
Yeah,
black box.
those are two very good questions. So let me try to tackle each of them one at a time. So for the black box dynamics, the reason for why I said that we can apply these methods to black box dynamics is because this loss function that I'm trying to optimize, this partial differential equation, which is my loss function in the case of neural reachability methods, do not rely on my ability to write down analytical dynamics in any way. As long as I can sample the states, and as long as I can tell what the dynamics vector will be at those states, I don't need to write or don't need a white box model of the system like we knew it in traditional sense. And so that's why I said like these systems, because they are data driven, can readily be applied to simulators. And that's all literally what we do. Rather than sort of using a function that is coded by us, we are just querying the simulator that given this state, given this control, tell me the next state. So as long as I can simulate that, I can actually compute this loss function and I can backprop through it.
And could you do that also with without the simulator, but with like a completely model-free thing, like you only have imitation learning data, teleop data or something? Or would that be a problem in terms of data, how much data you would actually need?
That's right. So in theory, we can do it, but then the problem will be the data problem, right? Because tally-operated data has two issues. A, it might be limited in terms of compared to simulation, because we might need to query simulation 1,000,000 times, and it will be very hard to have 1,000,000 samples with tally-operated data. Number two is I should be able to query the dynamics for any state and any control. Tally-operated data by definition has been collected through some policy, even though this policy is human-driven policy, nevertheless a policy underneath. And so I cannot really query the dynamics for any control I like. Maybe the right approach in that case is to use this tally-operated data and first convert it to some learned white box dynamics with perhaps some uncertainty bound. So we have also that method. So with the data driven, you can go two routes. You don't try to come up with a white box model first, and then you try to directly optimize the black box system. That's, I would say, is the right approach if you have a simulator available, meaning you can truly query the data or dynamics for any state, any control. If you can't do that, suppose when you have tally-operated data or some collected trajectories, I think the right approach to go is to learn a white box model first with uncertainty quantification, and then use that within the safety analysis. So we have both lines of work, depending on what's getting.
Yeah. Okay. Interesting.
And for LLM work, so let me quickly also answer that. In LLM work, the safety is actually learned itself. The safety definition itself is learned. So essentially, we have some data sets that are available. For example, ultra toxicity, beaver tail. These are some different data sets. And what these data sets have is that they have prompt and response. So these responses are in particular responses that are unsafe responses to these prompts. So what we are doing is we're encoding them into the latent space, and we are learning a classifier in the latent space based on this data. And that's what we are using as our definition of the failure set for that safety analysis.
Okay, interesting.
Same for diffusion model, by the way.
Okay, thank you. Alison, do you want to go next? Oh, sorry.
I was going to say Alison has her hand raised, so I'm going to.
Hello, thank you, Somil, for your presentation. So I was thinking, you estimate like the dynamics uncertainty and the environment uncertainty, but your safety filter couldn't have as well some uncertainty. So how you deal with this?
Yeah, that's a good question. So so to replay the question, there I'm handling dynamics uncertainty, but because my safety filter itself is learned, it could have errors or uncertainty. So in this work, so something that I did in present is for these neural reachability methods, we have developed conformal prediction based methods to actually calibrate the uncertainty in these neural output. So we can actually quantify the error in my value function. And so we are using those calibrated neural networks for coming up with the guardrails. They have some probability of failure because now these are probabilistic uncertainty quantifications, but we can control how much error there is in the neural network output if we want stronger safety guarantees.
Okay, nice. Thank you.
Yep.
Awesome. Are there any more questions? I think if not, thank you so much, Somil. This was really an awesome talk and great to have so much time for questions too. And thank you all for coming and for participating. And I hope to see you all at future TC events.
Thank
And
you, Frederica.
yeah, see you soon.
Thank you. Bye. Bye.
Bye-bye.
Thank you.